Hello again, everyone. I just wanted to provide a quick proof of the common segment theorem. So the common segment theorem here says that if you are given that AB and CD are congruent, then you get to claim that AC is congruent to BD. Right? So if you're given the outside segments are congruent, you get to claim that the overlapping ones are. And it also says that if you're given the overlapping segments are congruent, that AC is congruent to BD, then you get to claim that AB is congruent to CD. So given congruence of overlapping segments, you get to claim that the outside segments are congruent as well. So I'm going to do these individually, right? Well, in the two-column format, we always start with our given information, right? So we are given that AB is congruent to CD. Right. Well, if they're congruent, then we get to claim that their measures are equal. So the measure of AB is going to be equal to the measure of CD because that is the definition of congruence. The definition of congruence. Okay, and now we should make a little statement here to say that this middle segment here, BC, is equal to itself. Right? This is the reflexive property, is that the measure of a segment is going to be equal to itself. That is the reflexive property. Right? We're just making that statement because what we're going to do is we're going to add it to both sides. Right? So it's equal, so we can do that. Right? So if we add it to both sides, we can say AB plus BC is equal to BC plus CD. Right? We can add the same thing to both sides because that is the addition property of equality. The addition property of equality gets us there. And now, what is this? AB plus BC is, in fact, the segment AC. And BC plus BD is the segment BD because that is a statement of the segment addition property. I'm sorry, the segment addition postulate. Segment addition postulate gets us there. So we have that AC is equal to BD. And all we need to do is use the definition of congruence one more time. That definition of congruence gets us from the measure of those to the fact that the segments themselves are congruent. And there we've proved the first part of the theorem. All right. Now, to prove the second part, it's going to be very similar. Again, we start with the given information. Right? Given that AC is congruent to BD, right? This is given to us. And so we could then use the definition of congruence to say that, well, their measures are going to be equal. That's what congruent means. AC is equal to BD. All right. Now, we need to make a couple of statements about this. First, we could say that AC is equal to AB plus BC. That is another statement of the segment addition postulate. Just going to leave postulate off because I don't have enough room. But no, that's the segment addition postulate. I could also say that BD is equal to BC plus CD. Again, segment addition postulate tells us that. All right, now I can use substitution, the substitution property, to take these expressions that I just defined and replace them in this equation. So instead of AC, I'm going to use AB plus BC. That's equal to, instead of BD, I'm going to use BC plus CD. All right. Now, what I need to do is I need to subtract that BC away from both sides. Right? Well, it's the same piece, right? So we can use the subtraction property of equality to subtract those out. And then we would just have AB is equal to CD. And the last thing we need is the definition of congruence again. To claim that the segment AB is congruent to the segment CD. And there we go. We've proven both sides of the common segment theorem.